Hello and welcome to week 2 problem solving session for the NPTEL course on principles and applications of building science. So I'm Isha Rathod, PMRF and I am Isha Rathod, PMRF and Research Scholar at Department of Architecture and Planning, IIT Roorkee. And the course instructor for this course is Dr. Ilangovan Rajshekhar, who's the Associate Professor at Department of Architecture and Planning, IIT Roorkee. So this is week 2 problem solving session. So a few of the housekeeping rules for this session. Please mute yourself for the session. If you have any questions or if you want to post answers to the questions, you can do them in the chat box. I will moderate the chat box as we go along. And if you have any queries, you can raise your hand, unmute yourself for asking questions whenever I ask you for your, if you have any questions. So you can just raise your hand and unmute yourself and ask your questions. So, as we saw in the last week problem solving session also, the outline of the session is first we're going to look up at the highlights from each of the week where we talk about the key takeaways from each of the lecture units. And we also look up at the sample questions and calculations for the key terms. And we would look up at the assignment questions and the solutions to the assignment questions with their explanations. So these are questions which have been taken from the previous run of this NPTEL course. That is the 2022 run of the NPTEL course. And we will also look up at sample questions and calculations as we look in the highlights as well. And then if we received any queries from you relating to this week's content in the discussion forums, we will also address those queries here. So please use the discussion forums to post your queries and doubts and things on which you need more clarity, concepts on which you need more clarity. So you can list them there and we will try to cover them in the upcoming or the next problem solving sessions. So this week we looked up at bioclimatic design. In week 2, we looked up at bioclimatic design, the building envelope and thermal performance indicators for building envelope, as well as glazing systems and the energy efficiency measures for this. So let's look up at the highlights from week 2. So lecture 6, which was the first lecture in week 2, looked up at bioclimatic assessment. So here we looked up at the basics of bioclimatic assessment, as well as the demonstration of a software called Climate Consultant. So I will not go into the demonstration of the software. If we have time at the end of the session, we will look up at Climate Consultant as well. So by the basics of bioclimatic assessment is to look up at to determine the comfortable zone for the occupants of a building based on the climate variables, which are that is the ambient climate variables as well as their result on the indoor thermal comfort. So we have here the temperature and the relative humidity. And based on the movement of air that or the air speed, we determine the comfortable zone. So this is the comfortable zone. That is, it's between the temperature of 20 to 30 degrees centigrade, driver temperature, and between the relative humidity of 20 to 80%. And this is again within the wind speed of 0.1 meter per second. So if we increase the wind speed, the comfortable zone also increases. Even though the temperature is high, but because of wind speed, the effect is mediated. So this is the adaptive nature of the human thermal comfort. So with wind speed also it increases. Less than, so on the relative humidity scale, this is too dry if it's less than 20, and if it's more than 80, it's too humid. You will not feel comfortable if it's more than 80. So this is why these areas are outside the bound of the comfortable zone. This was one of the, so this is from the reference of climate responsive building, SCET 1993. Then we also looked up at, so similarly we have the relation for between the wind speed and what sort of radiation effect is also required. So this is just to define the base bioclimatic comfortable zone for the occupants for buildings. And similarly, this is on the psychometric chart. So we have relative humidity on the on these logarithmic sort of lines. So this is 100% relative humidity. That is, the air is saturated with moisture. And then as these lines go down, the relative humidity decreases to 0% on this axis. And then on the On the x-axis, we have the dry bulb temperature, and this is in Fahrenheit. Usually, we look up at the degree centigrade version of this. And then in the psychometric chart on the y-axis, we also have the humidity ratio, that is the amount of moisture present in the air, um, the humidity content basically. And then based on this, we have the thermal comfort zone. This is the thermal comfort zone. And then these are extended thermal comfort zone if we implement some of the passive or active design strategies. So for example, if we have high thermal mass, which is this zone, the comfortable zone increases between the temperature of 70 to 90 Fahrenheit, where it was earlier between 70 to 80 Fahrenheit only. So we get an increase of 10%, 10 degrees Fahrenheit more with increasing the thermal comfort. So each of the hours in your year can be plotted on this graph based on the temperature variables, outside temperature variables. And so the number of hours which fall in this comfort zone are the hours which are by default comfortable. That is, you don't need to implement any passive strategy or any active strategy for it to be sorry. So you don't need to implement any passive or active design strategy to achieve occupant thermal comfort. They are comfortable by itself, but a lot of the hours do not fall under this comfortable zone. So we need to implement passive strategies to increase the thermal comfort of the occupant throughout the year. So all of these lines are basically strategies which can be used to increase the thermal comfort of the occupant. So in the demonstration, in the lecture video, we also looked up at the climate consultant software, where the demonstration was shown on the number of hours and the number of comfortable and uncomfortable hours for a particular location. So these are the same design strategies. So as you move towards so this is high thermal mass, then this is high thermal mass with night ventilation. So if you open it during night, so thermal mass has this ability to store heat and to delay the time at which it comes inside. So if your outside peak is at 12 p.m., then the inside peak or the inside high maximum temperature is achieved at 2 p.m. So this time lag of 2 hours is how the thermal mass moderates the outside temperature to inside temperature. And it also causes a temperature reduction. So if the outside temperature, the maximum outside temperature was, let's say, 40 degrees centigrade at 12 p.m., then the inside temperature at 2 p.m., which is the maximum temperature, would be close to 36 degrees. So there's this degree difference because of the use of thermal mass. It does not allow that entire heat to come inside. It stores some of this heat. And when the conditions outside are favorable, it will release that heat outside. So to make those conditions favorable, especially in the extreme summer periods, we use another technique called night ventilation, which is basically opening the windows at night. So because the ambient temperature outside is lower during the night compared to the daytime temperatures, the heat which was stored can now be released to the outside night time period. So this is the second strategy, which is high thermal mass and night ventilation. So if we use both of these techniques, we can achieve a comfortable zone in this range. So a large number of your hourly data points will now be falling in this region, especially if the climate of your particular location is a hot, dry climate. So these techniques can be used. Then we have another technique which is called as evaporative cooling. So evaporative cooling is basically using for example, your desert coolers or water bodies. So they basically make use of the evaporation potential of water. So water absorbs the heat of the ambient and evaporates itself, causing evaporative cooling. So your desert coolers also work on the principle of evaporative cooling. And water bodies or courtyards filled with water bodies are another example of evaporative cooling phenomena. So with evaporative cooling, you can achieve a comfortable zone of this much. Even at higher humidity, you can achieve evaporative cooling potential and high comfortable zones. Then another strategy is comfort ventilation, which is basically having effective ventilation strategies like cross ventilation. That is, you have windows on opposite sides of each other so that the air flows through both the windows and does not get trapped inside the room. So that is comfort ventilation. Then we have internal gain, so which is from your computers or other appliances. They generate their own heat as well. So those internal gains can also be used to heat up your inside spaces. Then we have conventional heating. We have humidification for. So humidification causes thermal comfort in areas with low relative humidity. So you see this humidification achieves thermal comfort in areas with 40 less than 40% of relative humidity. So this is when you implement measures such that humidity is added to the air, because without it, the air itself is very dry. So the occupant will feel dryness and will not feel comfortable at this relative humidity level. So humidification is just adding moisture content to the air. So this is another area which can be added using a passive strategy. Then you have shade lines or shading for your open spaces. This is also applicable for winter months of the period. So if you see the when you actually plot the data points for each of the hours of your year for particular location, you will see that most of your winter months will fall in this zone because the temperatures are one on the lower side as well as the humidity is on the lower side. Whereas whereas the period for June to July, which is the monsoon periods in India especially, the data points will fall close to this area. And for your months, transitional months like April, March, and September, you will have comfortable data points here. You will have some data points for each of the months, some of the months in this comfortable zone by default itself. But a lot of strategies would need to be implemented to achieve a larger amount of comfort throughout the so this was the basis of the bioclimatic assessment. So using strategies to achieve thermal comfort. So this was what was discussed in lecture 6, which looked up at bioclimatic assessment. Then we moved on to lecture 7, where we looked up at thermal performance of building envelopes. So here we looked up at heat transfer through building envelopes and the fundamentals around it. So we also discussed this in the last week lecture briefly. So there are 3 modes of heat transfer. We have conduction, convection, and radiation. So conduction is when 2 bodies which are in contact with each other, and one body is at a higher temperature and the other body is at a lower temperature, let's say 40 degrees and 12 degrees. So the heat transfer will happen from the body of high temperature to the body of low temperature. So from 40 degrees centigrade to 12 degrees centigrade, this body 1 will try to transfer its heat to body with 12 degrees centigrade. So they will both try to achieve thermal equilibrium. That is, both of them will try to reach a common temperature because they are in contact. So they will try to reach a common temperature of, let's say, 22 in between. So this is conduction when both the bodies are in contact and the high temperature body tries to decimate or transfer its heat to the low temperature body. Then you have convection, which is which is done by bodies which are not in contact with each other, but which are when there is a medium like air or water between them. So that medium can be used for the heat transfer process. So convection in buildings is mostly through the air outside, the ambient air. So that is convection. Then we have radiation. So sun is like a radiator. So the radiation is basically emitting of rays or radiation to transfer heat. So every body has an emitting potential. So whenever they have absorbed heat, they will emit some of this heat back. So that is radiation. So the heat flow depends on a few factors. So this is one is the temperature difference. So for all of these heat transfer to happen, one body or there has to be a source which is at a higher temperature, and there has to be a receiving medium or the receiving object which is at a lower temperature. So, such that both of these bodies try to achieve thermal equilibrium. So temperature difference is the most important factor for heat to flow. Then you also have the surface area involved. If you have a larger surface area, more heat will transfer. If you have a lesser surface area, less heat will transfer. So surface area is also important when heat flow is considered. Then the amount of distance traveled by the heat. If the distance is much higher, then heat transfer will be less. If the distance is lesser, then the heat transfer is higher. and also the surface characteristics of these objects and the source. So, for example, for radiation, you need an emitting potential, which is also known as, which is denoted by E or emissivity, and also surface characteristics like absorptivity, which is the potential of the body to absorb heat. So that is also another surface characteristics this for this particular between the two surfaces for heat transfer to happen. So these are the four factors which affect the heat transfer process. And then two fundamental facts or two fundamental check laws, sort of you can say, are that two bodies are in thermal equilibrium when each other with each other when they have the same temperature. So the higher body will try to transmit all of its heat to the lower body such that both of them are in thermal equilibrium. That is, both of them achieve the same temperature. And in nature, heat always flows from hot to cold, which is 40 to 12. So from a higher temperature, it will always flow to a colder temperature until this thermal equilibrium is reached. So this is the fundamental knowledge for heat transfer. So we also looked up at the equations or the factors which affect the three type of heat transfer processes. So first we looked up at conduction or the conductive heat flow through opaque materials. So in this we have three factors which affect conduction. One is the U value or the transmission coefficient of the objects which are in conduction. Then we have the area of the surface. Then we have the temperature difference, which is delta T. So Q is equal to UA delta T. So Q here is the conductive heat flow only. We will also look up at the convective heat flow equation and the radiative heat flow equation as well. So conductive equation has three components, and all of them are directly associated with the conductive heat flow. That is, the U value, the area, and the temperature difference directly affects the U. So for high conduction to happen, the U value has to be high, the area of the surface has to be high, and the delta T, the temperature difference, also has to be high. So these type of questions, which are based on the relation between the equation terms, are can be expected in the examination for different equations, obviously. So you need to remember these equations. So Q is equal to UA delta T. This is one of the fundamental equations for conduction. So now we're going to look up at a numerical based on this equation. So you can try to post your answers in the box. So you basically just have to apply the formulas and see how it works. So okay, we will look at. Okay, so this is the question. So given that the area of the brick wall is 12 meters square, the U value of the wall is 2.13 watt per meter square Kelvin, and the maximum and minimum temperatures are 35 degrees centigrade and 18 degrees centigrade respectively. Calculate the heat flow through conduction for the brick wall. So in this equation, you just have to use the conduction equation, which we looked up in the previous slide. So which is Q is equal to UA delta T. So I will give you some time to try to solve this. You just have to use that equation. Questions like this can be expected in the examination and in the assignments as well. So this will directly help you. I'm going to wait here for a few minutes so that you can solve this. Okay, so we have one answer. Okay, so we will look at this. So the answer is correct, exactly. So Q is equal to UA delta C. So Q, we are given the value of U as 2.13 watt per meter square Kelvin. Then we have the area as 12 meters square. And then we converted the units of the temperature to Kelvin because our U value was in Kelvin. Although because it is delta T, and delta T can be degree centigrade or Kelvin, because Kelvin is just adding 273 to the degree centigrade equation. It does not directly affect the outcome of your result if you don't convert it to Kelvin and just use delta T for degree centigrade also. So we converted it into Kelvin, the temperature, highest temperature 35 degrees 308 and 18 degrees 291 Kelvin. So then we solve these equations and we get 434.52 watt, which is the correct answer. So again, remember the units. Sometimes these units can affect your calculations. Also, if you took delta T first and then try to convert that difference into Kelvin, it will also result in a wrong answer. So this is how you solve the equations. Okay, and then two things which I forgot to mention in the slide after this was the one is the conductivity, which is again the surface property of a material. So this is the heat flow through a material per unit thickness, and then we have conductance, which is the heat flow through a material of the stated thickness. So so we have conductance is defined as the conductivity divided by the thickness of the material or the unit thickness. So conductance is one of the fundamental properties of the building envelope. But for thermal calculations, we look up at the for thermal calculations, we look up at thermal transmittance or the U value, which is also one of the fundamental indicators used for measuring the thermal performance in as per the National Building Code as well as the other standards, especially in India. And thermal resistance, which is the ability of the material to resist the heat which is coming, is uh, is the inverse of conductance. So resistance is 1 by C. And so we looked up at this equation. So again, these videos will be available online. So if you miss a session or if you want to go through the questions or the answers which are covered in these sessions, you can look up at the YouTube video links. I will share them in the discussion forum again. So now we look up at thermal transmittance or U value. So thermal transmittance is nothing but the sum of the R values. So R values, we consider both the inside and the outside surface film coefficients, which are nothing but the layer of air, which sort of, if to have an analogy associated with the understanding the surface film surface coefficients. So, for example, the layer of sweat which forms upon skin is a sort of equivalent to the that's a similar sort of layer forms up outside the building envelope. So this is basically the air layer. It's a very thin film. So these are basically represented by the film surface coefficients, which is H naught and Hi. So the sum of resistance is basically 1 by H naught, which is the outside air film coefficient. And then R1, which is the resistance of layer 1, R2, resistance of layer 3. So again, the building envelope can be made up of a number of layers. So we consider those number of layers as well as two different distinct layers, which is the outside air film and the inside air film. So 1 by H naught is outside air film, R1 is resistance of layer 1, R2 is resistance of layer 2, and so on, as many number of layers as you have for your envelope, plus 1 by Hi, which is your indoor air film coefficient. And then U or thermal transmittance is nothing but 1 by delta R. And the unit for U value is watt per meter square Kelvin. So this is the fundamental indicator which is used for measuring and assessing the thermal performance for building envelopes. So next we look up at an equation which looks up at how to derive the U value for the building wall assembly. So we have the question, we have three layers. So calculate the U value of a brick wall configuration given below with both side plasters. So we have brick 200 mm. Then we have dense cement concrete 15 mm on both the sides. So a total of 230 mm brick wall we have, which is plastered on both the side. And we are given the inside film coefficient Hi as 9.36 watt per meter square Kelvin. And we are given the outside film coefficient H naught as 19.86 watt per meter square Kelvin. And we are given the thermal conductivities of the materials. So resistance of the material is determined by the thickness of the material divided by its thermal conductivity. So Li by Ki. So we have thickness as Li and thermal conductivity as Ki. And we are given the film coefficients. So you can, I will pause for a few minutes so that you can solve these equations. When you once you solve the equations, you can post your answers in the chat box again for the people who have recently joined. So I will pause here for a minute. You can try to solve the equation. Okay, so we will try to look up at. So first we drew a schematic diagram for the wall assembly. So we determined outside and inside. Then we consider the outside film layer. Then we have our dense cement plaster, which is 15 mm. Then we have the brick wall, which is 200 mm, followed by another layer of dense cement plaster and the inside film layer. So this is our schematic diagram. So now we keep our schematic diagram together so that we have a better understanding of the layer position. And then we use the equation. So U is 1 by delta R. And delta R is calculated as 1 by H naught plus the resistance of layer 1, which is basically the thickness of layer 1 divided by the thermal conductivity of layer 1, plus thickness of layer 2 divided by thermal conductivity of layer 2, plus thickness of layer 3 divided by thermal conductivity of layer 3 plus 1 by Hi. So again, make sure that all of the units are correct. So temperatures in Kelvin and thickness is expressed in meters. All of the units are similar basically. And then we input the values which were given. So outside the air film coefficient is 19.86 watt per meter square Kelvin. So 1 by 19.86 plus thickness of the cement plaster is 15 mm. So 0.015 meter divided by its thermal conductivity, which is 0.721 watt per meter Kelvin, plus 200 mm brick wall, 0.2 meter thickness divided by 0.811 watt per meter square, its thermal conductivity, plus again the dense layer concrete, 0.015 meter divided by 0.721 watt per meter Kelvin, and then the inside film coefficient number plus 1 by 9.36 watt per meter square Kelvin. So on solving this equation, we get a U value of 2.242 watt per meter square Kelvin. So our U value for the given wall configuration was 2.242 watt per meter square Kelvin. So this is how you basically solve the questions around U value. So I'm sure there's one question on U value calculation in your assignment too. So you can use this example as a case for the answering that question as well. So this is how the calculations are done. So moving on to our second heat transfer process, which is convection. So convection is the heat transfer to convection is given as pH, and this is again expressed in watts. And this is equal to the heat transfer coefficient expressed in watt per meter square Kelvin or watt per meter square degree centigrade. So again, a lot of these heat transfer coefficients are based on temperature difference. So degree centigrade and degree Kelvin can be used inter-separatively for it. But if you have to use Fahrenheit, you have to do that conversion. And then this is also directly proportional to the area contacting the fluids. So area is again the second parameter. And then we have the temperature difference. So this is similar to the conduction equation as well, where we instead of heat transfer, we have U. A is similar, or the areas which are in contact, or the areas which are contacting the fluid or the medium here. And then again, the temperature difference between the fluid and the area. So this is similar. So you just have to remember for convection, this is heat transfer coefficients, and for conduction, it's U value. But all the terms are directly proportional to the convective heat transfer flow. So for a higher conductive heat transfer flow, the heat transfer coefficient has to be high, the area has to be high, and the temperature difference has to be high. So this is convection. So you will not look up at convection because this is a similar equation to conduction. So you can solve a convective heat transfer flow examples also similarly. So in convection, we have two types of convection. So one is free convection, where the flow of gas or liquid comes from the differences in density and temperature. That is, you don't have to have a active measure or a electricity driven or a mechanically forced mechanism for the flow of air or the flow of liquid. So they flow by itself because of the differences in their densities and temperatures. Whereas for forced convection, you have to use mechanical measures. So the flow of gas or liquid is circulated by pumps or fans. So that is mechanical or forced ventilation. So as per the standards, fans are not considered as forced or mechanical ventilation, but your HVAC is a forced convection flow. Your natural opening of windows is a free convection flow. So these are two examples of the different types of convection. So convection also depends on the speed of the fluid movement. So if you want a higher speed, you have to use a mechanically forced convective measures or a forced convection measure. Okay. So next we look up at radiation. So radiation is heat which is transferred by electromagnetic waves. So thermal radiation is electromagnetic waves. Now these can include light as well as heat waves, which are produced by objects because of their temperature. Usually, a higher the temperature of the object is, the more thermal radiation it gives off. And as the temperature rises, thermal radiation produces shorter wavelengths. So we have shorter wavelengths and longer wavelengths, which is the distance required for it to travel a particular distance. Uh, the time required basically. So that's the wavelength of the thermal radiation. And radiation depends on the temperature and surface area again. So we looked up at the factors which influence all the three type of heat transfer processes. So temperature and surface area are common to both of them. And surface characteristics was one, and one more was there. So you can refer to that as well. So this is also radiation. So for radiation, the equation is power, which is watts. So the heat transfer through radiation is also expressed in watts again similarly. Then we have the Stephen Boltzmann constant, which is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. And this is also again directly proportional to surface area and temperature to the power of 4. So we this temperature is actually absolute temperature. This is not the temperature difference, and this absolute temperature is expressed in Kelvin. So this is basically the amount of heat the body is giving out in the forms of radiation. So again, the temperature is not temperature difference. It is the actual temperature of the body which is emitting these radiations, and the surface area of the body which is emitting these radiations. So these terms are common. So basically, the power of the terms can vary, but you see that temperature and area are the two recurring factors or parameters which come in all the three heat transfer processes. The only difference is in terms of the constants or the calculated value of U value and other things. So similarly, radiation equations or radiation numericals can be solved based on these equations. So these are very straightforward equations. You just need to remember, usually the S value or the Stephen Boltzmann constant is also given in the numericals, but you can remember these values for your constants and the formulas as well. So again, for radiation to be higher, for that is for the heat transfer by radiation to be higher, the surface area of the body, emitting body should be high, as well as the temperature at which the body is high. So this is radiation. And then there are two terms, which is the absorptivity and the emissivity of the objects or the bodies. So these are also used for the surface facade, and these are basically the surface characteristics of the body. So if you remember, we looked up at factors which affect the heat transfer. So we had surface characteristics. Both of these factors are the surface characteristics of the objects or the facades. So absorptivity is the main factor in determining the temperature response to shortwave solar radiation, and this is largely dependent by color. So absorptivity is expressed in the ratio between 0 to 1, and a white body has an absorptivity of close to 0.6. And for different colors of the walls, we have different absorptivity. And similarly, emissivity is the main factor which determines the response to long wave radiation. So remember, absorptivity is to short wave radiations and emissivity is to long wave radiations. And this is so generally for non-metallic surfaces, emissivity is taken as 0.9. And both absorptivity and emissivity, so they are represented by the letter A and E, are properties of a material which determine the radiant exchange of a surface with its environment. So exact values again depend on the wavelength of the emission or the wavelength of the radiation. Okay, so both of these are factors which affect the building performance directly. Then we look up at thermal insulation. So thermal insulation can be of three types. We have resistive, reflective, and capacitive. So these are basically the responses to radiation which we see. So you can resist or stop the flow of heat by preventing it. Then you can reflect a part of this radiation which is being received. If you have a shiny or a metallic surface, you are going to reflect a part of this radiation. And capacitive is when you store this radiation within yourself and then release it outside. So these are basically the type of insulation or building materials response to how they address radiation which is falling on it. So all the envelopes do all these three type of responses. The only thing is that one or two of these responses will be more pronounced compared to the other two. So for resistive, we have something like an insulation or a thermocol board, or the what do you XPS, extruded polystyrene board. So those are resistive type of thermal insulations. Then we have reflective materials like aluminum panels and things. Then we have capacitive insulation materials like your brick walls or your concrete walls. So these are the three types and their examples. So moving on to lecture 8 to 9, we looked up at the thermal performance of building envelopes and the indices and measures. So both of these lectures looked up at the thermal performance of building envelopes. So both of them are covered together. And particularly we looked up at indices and measures and their numericals on how to solve them. So how do we assess the effectiveness of the envelope's thermal performance? So the thermal efficiency of an envelope can be measured at three different levels. So we have the element level, then we have the component level, and we have the assembly level. So element level is something like your individual layer. So component level is the entire building envelope, all of the layers acting together. And assembly level is all of your components acting together. So the entire building is is at the assembly level. Then your component is your U value for just your building facade or your building wall. And then element level is just your thermal conductivity of your particular layer. So these are examples of how thermal efficiency of envelopes is measured at three different levels. And then because most of our especially if we look from an Indian perspective, we don't look up at the hydrothermal efficiency of the building enclosure. But for especially for buildings in Europe and UK, which are usually built with which are more towards the wood type construction, moisture content is also an important factor in assessing the building performance or building thermal performance. So there, the hydrothermal efficiency of the overall building enclosure is also an important aspect of assessing the effectiveness of the building envelope. And then the air tightness of building exposures is also one of the important factors. So, for example, your building can have leaks or because of poor workmanship, there could be gaps around your windows from where air can be coming in. So these are very small gaps, but they affect the thermal performance of your building, especially in winters when you want the heat and uh, the heat from the inside to not escape out, because the outside is at a lower temperature and it will transfer heat from inside to outside, as well as your wind will flow in from outside through through these gaps or leaks in your building construction. So there, air tightness is also a very important factor for envelope thermal performance. So in India, we do not give in Indian building construction, we do not give importance to both moisture content and air tightness as much as it is given in the European and the UK context. But these are also two important aspects which need to be considered for your thermal performance for buildings. Then again, for element level properties, we need to have a primary idea about the thermal resistance to heat flow. So, for example, thermal conductivity is an element level property. Then for component level, you need to have more precise idea about the thermal performance. So your thermal transmittance or U value is one indicator. Then at assembly level properties, you need to have a clear picture of all the for the assembly level properties, you need to have a clear picture of all the thermal behavior aspects. So it includes all resistive, reflective, and capacitive types and how they behave. So next we look up at the indicators which are mentioned in the National Building Code of India. So the National Building Code of India and the Standard Procedure 41 or SP 41, which is one of the codes which look up at the thermal performance of buildings specifically. Both of these codes refer to a few of these indicators and measures for assessing the thermal performance of envelopes, and they give certain recommendations and benchmark limits for all of these values. So we look up at recommendations for U value for the wall. So for U value for each of the different climatic zones of the country, that is the 5 different type of climatic zones we have for walls and for roof, the U value recommendations are given for the different climates. That is the minimum and maximum U value for walls and roof in all of these climates are given. Then we also have thermal damping, which is based on the outside temperature and the inside temperature ranges. So thermal damping is basically the amount of damping or the reduction in the reduction between the outside temperature wave and the inside temperature wave. So this is again calculated by the ranges of the outside temperature and the inside room temperatures. So that is thermal damping. Then we have the thermal performance index or TPI, which is based on the surface temperature of the walls. So TPI of uh, then again TPI ranges are given and they are categorized into good, very poor, and very poor. And then we have the thermal time constant, which is again an indicator which is expressed in hours. And we have building index. So all of these five properties are the five indicators and measures are mentioned in the National Building Code of India and used for assessing the building envelope performance. Now we will look up at all of them. So we looked up at the calculations for U value previously. So we will look up at the other factors also. So what you see here is the outside surface temperature or the solar temperature. So solar temperature is the combined effect of both the outside air temperature as well as the solar radiation outside. And the smaller wave is the thermal damping. So if you see, there is a visible time lag. So the peak of the outside temperature and the peak inside is at a different temperature, is at a different time. So your x-axis is time and your y-axis is temperature. And if you, for the massive wall, there's always going to be a time lag, which is equivalent to, let's say, 2 hours or 1 to 2 hours, basically. So your peak is going to be delayed by 1 or 2 hours because of the massive thermal construction which is present. And you also see the difference in the magnitudes of temperature. So the outside temperature is much higher compared to the inside temperature. So this is actually the thermal damping effect. So if you basically, if you push the outside temperature layers on both sides and sort of squeeze it, that is the thermal damping effect. That is, this is the percentage by which the building construction has dampened the outside temperature waves. So thermal mass especially does both of this. That is the time lag as well as the thermal damping. So thermal mass is basically materials which have the capacity to store thermal energy for extended periods. And these are usually constructions like your stone wall, your thick masonry, or your thick brick wall, your concrete wall. So they store heat for a longer period of time, and then they release it either to inside or outside wherever the temperature is lower based on the heat transfer process. And then, so basically, they cause this time lag because they are storing that heat and delaying that heat to transfer in to your indoor spaces. So that is why time lag is happening. And because this heat is being sort of transferred through these different layers, the amount of heat which is transferred to the different layers gets reduced because each of these layers have a storage potential. So again, the amount of heat which reaches inside is much lesser compared to the heat which was gained on the outside surface. So thermal mass is used effectively to absorb the daytime heat gains, that is reducing the cooling load. So if you reduce the daytime heat gains, you do not need the same amount of air conditioning required. So you basically reduce your cooling load and release the heat during the night, reducing the heating load. So yeah, so in winters also you do not, when you use thermal mass, you do not need to spend extravagantly on radiators and heating devices. Your thermal mass itself acts as a heat source for you during winters, whereas it acts as a heat. Um, it does not allow heat to come in during winters. So that is thermal mass. So now for the calculations of the two indicators, that is the decrement factor and the thermal damping. So decrement factor is nothing but the inside maximum temperature, the room driver temperature, minus the inside minimum temperature, which is both the maximum temperature inside and the minimum temperature inside. So this point minus this point, that is this temperature difference, divided by the outside maximum minus the outside minimum temperature. So both of these are again driver temperatures. So outside maximum minus outside minimum temperatures. So this range. So this is basically the range of inside temperature to the range of outside temperature. That is your decrement factor. And then thermal damping is nothing but delta TO, which is your outside temperature range. Again, T outside max minus T outside minus your delta TO, minus the delta Ti, which is the inside temperature range. The inside maximum temperature minus inside minimum temperature divided by the delta T or the outside temperature range into 100. This is your thermal damping effect. That is the percentage by which the uh, outside temperature wave is being dampened. So now we will look up at numericals to calculate both the decrement factor and the thermal damping. So after I introduce the numericals, you can take some time to solve these numericals and post your answer in the chat box again for the newly joined people. So the question is to calculate the decrement factor for a west wall for a given material. And we are given the maximum and minimum outside temperatures as 46.5 degrees centigrade and 29.5 degrees centigrade. And the inside maximum and minimum temperatures are 38 degree and 32.8 degrees centigrade respectively. So you just need to calculate the decrement factor. This is just the the inside maximum minus minimum divided by the outside maximum minus minimum temperatures. So I will pause here so that you can solve the questions. Okay, so this is a very straightforward application for the of the equation. So we have the maximum inside temperature minus the minimum inside temperature on the numerator. So we subtract 38 minus 32.8, which is our inside maximum and minimum temperatures respectively. And then we have the outside maximum and outside minimum temperatures subtraction in the denominator. So we have 46.5 outside maximum and 29.5 outside minimum. So we get 5.2 by 17. So we get a decrement factor of 0.306. So this is how you calculate decrement factor. So the wall given to us was a west wall. So the decrement factor for the given wall of the given material is 0.306. That's our answer. So it's a direct application of the formulas. Okay. So again, decrement factor is directly proportional to the difference in inside surface temperatures and inversely proportional to the difference in outside temperatures. So if the difference or the temperature range of outside temperature is higher, your decrement factor is going to be lower. Okay. So next we look up at the calculation of thermal damping for the same wall. Both of these values are both of the maximum and minimums for inside and outside temperatures are same. So you just have to calculate thermal damping. So decrement factor is a unitless fraction, whereas thermal damping is expressed in percentage. Again, this is a very straightforward, just direct application of the formula given for thermal damping. Okay, so we have an answer. Okay. Yes, it's close to this only. So thermal damping is delta T outside minus delta T inside by delta T outside into 100. So we have 46.5 minus 29.5 are outside temperatures maximum and minimum subtracted by the delta Ti, which is 38 minus 32.8 divided by again delta To. into 100 because this is expressed as percentage. So this is 17 minus 5.2 by 17 into 100. So we get 69.41. So the thermal damping of this given wall of given material is 69.41. So it dampens the outside temperature wave by close to 70%. Okay. So this is how you calculate these thermal damping and decrement factor, which are two measures for looking at the thermal performance of building envelopes. So the ranges for both thermal damping and decrement factor, maximum, minimum are given in NBC. So I think I have slides for them as well later. Then another indicator is the diurnal heat capacity. So this is basically the measure of the building's capacity to absorb the solar energy coming to the inside spaces and the ability to release that heat to the interior during the nighttime hours. And this is particular importance of buildings with direct solar gain. So your buildings which have larger windows or which have a direct entry for your solar heat, which allow direct solar heat gain. So it's particularly important or used in those type of buildings. So now the diurnal heat capacity is expressed as a function of the building's materials density, the building material specific heat. That is all of these layers which make up your building envelope. Uh, all of those layers, density, specific heat, conductivity, and the thickness of those layers. And the total diurnal heat capacity of the building is calculated by summing up all of the diurnal heat capacity of all of these layers, which are exposed to the interior and the outside air. So I'm sure you would have solved this equation in the slides also. So the required heat capacity for walls can be derived by taking the outdoor temperature range. So if we know the outdoor temperature range, the absorptivity of the surface or the absorptivity of the wall, and the maximum solar intensity into consideration, we can calculate the required heat capacity for the wall. And then we can check if the required heat capacity of the wall is being matched by any of the existing building materials, and we can directly use those materials in our buildings. So the equation for the required heat capacity, and this is given by Baruch Givoni in one of his books. So Q required is 2.5 times the difference between the outside maximum and outside minimum. That is your outside temperature range, plus 0.1 absorptivity into Imax, or your maximum solar intensity. So we will now solve a numerical based on the required heat capacity for the wall for a particular location. Okay, so the question is that your average outside temperature range, which is your T out maximum minus T out minimum for Ahmedabad, is found to be 13 degrees centigrade, and the Imax or the maximum solar intensity is found to be 925 watt per meter square. So can you calculate the required heat capacity of a wall for Ahmedabad? So we are going to take the absorptivity as 0.3 here. Forgot to mention the absorptivity. So let's take the absorptivity as 0.3. So the equation is very straightforward. 2.5 times T out minus T out max minus T out min plus absorptivity into Imax. 0.1 into absorptivity into my Imax, yes. And absorptivity is 0.1. So I will wait for you guys to solve this equation. Okay, so Q required is 2.5 times T out max minus T out min, and plus 0.1 times the absorptivity into Imax. So we have Q required as 2.5. Our delta T outside is given as 13 degrees plus 0.1. We took absorptivity as 0.3, and our Imax is 925 watt per meter square. So we get a Q required of 60.25 watt hour per meter square degree centigrade. So the required heat capacity of a wall in Ahmedabad is 60.25 watt hour per meter square degree centigrade. So now we see that a reinforced concrete wall has a heat capacity of 86.4 watt-hour per meter square Kelvin, which is higher than the required heat capacity of a wall in Ahmedabad. So the RC wall can be directly used in Ahmedabad, and its thermal performance is going to be equivalent to the required heat capacity. Okay, so this is the practical implication. So how you can select materials based on the required heat capacity can be calculated like this. So moving on, so thermal time constant is another indicator which is used for measuring the thermal performance of building envelope. So this is basically the amount of time it takes for the heat to go from outside to inside. So thermal time constant, also known as TTC, and this is expressed as the sum of Q by U. Q is the heat divided by the U value, and so it's a little complicated to understand in terms of the equation. So we have this is the sum of 1 by F naught, which is the outside film coefficient again, plus the Ln, or the thickness of layer, divided by 2K, which is the thermal conductivity of the layer, into the thickness, density, and thermal specific heat capacity of your each of the layers. So we will look up at the solution to the a formula on how to calculate thermal time constant. So this can be used for composite as well as uh, homogeneous walls, that is walls which are made of a single material, and walls which are made of more than one layer materials, composite and homogeneous. So thermal time constant is dependent on thickness, conductivity, density, and specific heat of each of the layers of the building envelope. Okay, so now we will look up at an example on how to solve for thermal time constant for the brick wall. Similar brick wall which we saw for calculating the U value. So calculate the thermal time constant, or TTC, of a brick wall configuration given below with both sides. So we are given the thickness, thermal conductivity, density, and specific heat for each of the layers of the wall. So again, we have 15 mm plaster with 200 mm brick, and then again 15 mm plaster. It's a little tricky to solve this, so I will just go to the solution. So this is our brick wall which we see. Then, so TTC is calculated as Q by U. If you know the heat stored, you can directly divide it by U. But since we don't know the Q value, we are going to solve it using the outside film coefficient plus the properties of each of the layers, thickness, density, conductivity, and specific heat. So for layer 1, we are using gray color, and for any factor which is related to layer 1. For layer 2, we are using the red color, and for layer 3, we are using the yellow color. So we go from outside to inside. So layer 1 is the outermost layer, layer 2 is the middle layer, and layer 3 is the innermost layer. Okay. And this equation continues to n number of layers. Okay. So now the equation is 1 by F naught, which is the outside film coefficient, plus thickness of layer 1 divided by 2 times thermal conductivity of layer 1 into thickness of layer 1, density of layer 1, specific heat of layer 1. This is this is the factor which corresponds to layer 1. When we go on to layer 2, we have 1 by F naught, which is our outside film coefficient, L1 by K1, thickness of layer 1 divided by thermal conductivity of layer 1. So in the second layer, the L1 by K1 is not divided by 2. So this is not 2K1, this is just K1. Similarly, for layer 3, it will become K1 and K2. Only for the layer which we are talking about will the factor L2 by K2 will be like 2K2. Okay, so thickness of layer 1 divided by thermal conductivity of layer 1 plus thickness of layer 2 divided by 2 times thermal conductivity of layer 2 into thickness of layer 2, density of layer 2, and specific heat of layer 2. Plus, for the third layer, which is again a dense concrete layer, we have 1 by F naught, our outside film coefficient, plus thickness of layer 1 by thermal conductivity of layer 1, thickness of layer 2 by thermal conductivity of layer 2, and thickness of layer 3 divided by 2 times thermal conductivity of layer 3 into layer 3 thickness, density, and thermal conductive specific heat of layer 3. Okay. So L is thickness, K thermal conductivity, low density, and C specific heat capacity. Okay, so this is the equation. So if you have more number of layers, for each of the layers, you will have an introduction of the previous layers L1, K1. So for layer 3, we have both for L1 and L2, layer 1 and layer 2. And you will have a term for the specific layer itself, but it will be 2K. Okay, so this is important to remember. So now when we solve for TTC, we just put all of these values and check that the units are correct. So if, the outside film coefficient is 19.86. Thickness is again put in meters, 2 times conductivity watt per meter Kelvin. And then the L1, O1, C1. So thickness, density, and specific heat. So specific heat was given to us in kg per kilojoule per kg Kelvin. So we have converted kilojoule to watt seconds. Okay, so 1 kilojoule is 10 to the power 3 watt seconds. So we had 0.86 kilojoule per kg Kelvin. So instead of kilojoule, we have multiplied it by 10 to the power 3 watt seconds. Kg per Kelvin is same. Okay. Similarly, this conversion is done for all the 3 layers wherever this specific heat capacity term has come. Okay, for each of these layers. So remember, 2 things to remember. For each of the different layers, you will have a component of your previous layer, which is L1 by K1. For layer 3, you have L1 by K1 and L2 by K2. And for your particular layer for which you're putting that term, you will have Y2, K2. Then you have to remember the conversion of units to watt seconds. Okay, so after putting all of these values, we just solve we get the values in meter square Kelvin per watt into watt second per meter square Kelvin. So again, a few of these terms will go out and this will just come in seconds. Okay, so we solve it for all of these 3 layer terms. So this is for layer 1, this is for layer 2, and this is for layer 3. So when we solve this, we get TTC as 70,198.82 seconds. Okay, so then we convert these seconds into hours. So 1 hour is 3,600 seconds. So we get a TTC of close to 19.5 hours. Okay, so TTC is expressed in hours. So you'll get the answer in seconds. You can convert it to hours. If your question demands an answer in seconds, you can put it in seconds also. But TTC is expressed in hours usually. So the thermal time constant of a 200 mm brick wall with 15 mm plaster on both sides is close to 19.5 hours. Okay. So this is how you solve for TTC. I know it's slightly complicated, but that is how the formula works. And this is the amount of time it takes heat from outside to reach inside completely. Okay, next indicator is the thermal performance index or TPI. So TPI is expressed as the inside surface maximum temperature minus 30 by 8 into 100. So it takes 30 as a base case. So if the temperature rises above 30, so a temperature of 38 is equivalent to a TPI of 100%. So then they based on SP41 and NBC also, we have the TPI values ranges. So if your TPI is less than or equal to 75, it is good. If it's between 75 to 125, it is fair. If it's between 125 to 175, it is poor. If it's between 175 to 225, it's very poor. And if it's more than 225, it's extremely poor. And they are rated in the TPI class of A, B, C, D, and E based on these quality of performance values. So you, for building envelopes, it's essential for the TPI to be in the range of A to B. That is, TPI can be less than, should be less than 125 mostly. Okay. So the TPI calculation is again, so this is for naturally ventilated building. For AC buildings, it it is expressed in terms of peak heat gain, which we have not discussed here, but there's a separate equation for AC buildings calculation of TPIs. Second. Okay, for calculation of TPIs. Okay, so TPI is usually calculated for the west wall. And once, if you want to calculate it for the different wall, let's say for the south wall, you have to use a correction factor. So for calculating the corrected TPI or for calculating TPIs for walls other than the west wall or for the roof, you have to do TPI minus 50, which is the TPI value which you got, minus 50 into the, this is the correction factor. This is also determined from a table which is given in SP41 and NBC both, plus 50. Okay, so we will look up at calculating TPI also in the next few slides. Okay, so calculate the TPI for A west wall, and B, a north wall in a naturally ventilated building in hot, dry climate zone for the given material with maximum inside surface temperature as 39.4 degrees centigrade. Okay. Okay, so to calculate this for west wall, we just calculate TPI. So our TPI is Ti max minus 30 by 8 into 100. So TPI is 39.4 minus 30 by 8 into 100. So this is 9.4 by 8 into 100. So this is 117.5. So this falls in the category of fair TPI class B. Okay. And then for north wall, we calculate TPI as 39.4 minus 30. We calculate this TPI value for west, which is 117. Then we use the corrected equation. So for north wall from the table, I took the value for C. So this is 117.5 minus 50 into correction factor, which is 0.45 for north wall for the hot dry climate. So we get a TPI of 80.38, which is again TPI class B. Yeah, so correction factor is 0.45. So you have a table from which you can read those values. Okay, so in SP41, we are again given values for all of these terms which we looked up at for the different climate zones. So we have the maximum U value for the roof and for an exposed wall as 2.33 for roof and for exposed wall 2.56. We have TPI maximum. So this is for hot, dry and hot humid zones. Then for the TPI or the thermal performance index, we want to have a TPI between 100 to 125. That is class A, class B. Okay. Then this is our thermal damping. No, this is our TTC, which is expressed in hours. So we have a TTC, minimum TTC for roof is 20 hours and for wall is 16 hours. And then D, thermal damping. So minimum damping is 75% in roof and 60% in walls. That is, your wall should do at least 60% thermal damping of your outside temperature wave. Okay, similarly, you have the benchmark values for warm humid zones. So the building designers and contractors try to follow these standards and getting approvals for their building projects. And these are the benchmarks or limits set up by the National Building Code as well, which refers to SP41 for the same. Okay, so now, okay. So what should be the values of thermal performance standards for the wall in hot, dry climatic regions? So we are given this table, so you can directly read for your hot, dry climate region, these range of values apply. So for your walls, the values are a maximum U value of 2.56, maximum TPI of 125, that is, it should be lesser than or equivalent to class A or class B. TPI, your thermal time constant should be minimum 16 hours, and your minimum thermal damping should be 60%. So this is how you read the tables, and these are the values you should try to achieve in your buildings in a hot, dry climate region for your walls. Similarly, for those the above values. Okay, and then this is the building index, which is again an indicator used for limits of building index corresponding to air temperature and comfort limits. So we try to have a building index of less than 50 only, which that is between 0 to 50 only. based on an indoor temperature of 32 degrees. And this is the comfortable conditions with a fan. And beyond this, you need to use mechanical measures to cool your buildings. So these are indicators which are mentioned in the National Building Code. So the Singapore Building Code mentions another indicator, which is RETV, which looks up at the window wall ratio and the U value of your windows as well as your facades and correction factors and other things. So this is also discussed in the video RETV, but this is based on the Singapore building standards. Okay, so it looks up at three things, which is your heat conduction through your opaque walls, then heat conduction through your glass windows, as well as the solar radiations through your glass windows. So this first component is based on your opaque walls. So this is heat conduction through your opaque walls, and this is through your glass windows, and then your solar radiation through glass windows. So this was all which was covered in lectures 8 to 9, which look about thermal performance of building envelopes. Next, we look up at lecture 10, which was on glazing and shading systems. So here we looked up at thermal properties of glazings, especially four factors basically. So thermal efficiency of your glazing or glass systems or window systems is driven by the thermal transmittance of the glass, the solar heat gain through the glass, the thermal transmittance of the frame, because frame also plays a, so glass is sort of an insulation, whereas frame is made up of aluminum panels or aluminum frame, and then the air tightness of the glass frame assembly. So these four factors affect the thermal efficiency of your glazing systems. So the glazing U value is the heat transfer to conduction through your windows. Then you have the SHGC, which is the ratio of solar heat gain through the glass relative to the incident solar radiation. That is the amount of heat gain through glass divided by the total solar radiation which is being incident on your window. And this is expressed in the ratio of 0 to 1. And it includes solar energy, which is directly transmitted through the glazing. And it also includes the energy which is absorbed by the glazing and subsequently converted and thermally radiated inwards. So both of these values are included in the SHGC, solar heat gain coefficient. Okay. Yeah, so solar heat gain coefficient, SHGC. So this is improved by shading devices, and it minimizes the incident direct solar radiation. And these are usually calculated based on for your low E glasses. So you want to when you select glasses, you look up at the SHGC value, as well as other terms like visible light transmittance and the U value of your glass. So this is how you select glasses for your to be put in your buildings. And then there are certain challenges to implementing the performance of fenestration in the calculation of thermal performance in buildings. These are basically determining the center of glass U value. So over the years, the value of the glass goes through certain processes and the U value changes basically. So there is the challenge of determining the U value for your glass, and then how to include the frame U value into the same thing. And then the effect of infiltration and other things, the computation of the whole assembly U value, effect of shading on SHGC, and steady state computations versus dynamic on-site performance. So a lot of these indicators are calculated based on steady state computations. All of these formulas are based on certain assumptions, which are usually steady state, which consider that the heat transfer process is happens in instances in one time frame and concludes in another time frame, whereas the actual thermal performance of buildings is dynamic. That is, it keeps changes every second because the ambient conditions keep changing every second. But for ease of calculations and computations, we use steady state analysis. So all of these formulas and equations which we looked up at were steady state calculations. But the actual thermal performance of buildings is correctly determined by dynamic analysis, which is usually what is done through simulations. So that is one of the other challenge with glazings as well, because it again deals with both solar radiation as well as the outside temperatures. So we also looked up at the shading design and systems. So we looked up at the angles, which we also looked up at in week 1. So shading requirements vary according to your climate, latitude, the facade orientation, and the actual shading requirement. And the angles, altitude, azimuth are used for calculating the shadings. So there are also other angles like wall azimuth, horizontal shadow angle, and vertical shadow angles, which are discussed in the video. You can go through that video. There is also lecture 11, which is in week 3, which looks up at design of the shading system. So both of them should be looked up at together. And then you have the horizontal shadow angle, which is basically for your vertical shading devices. So if this is your window and this is your vertical shading device, this is your HSA, which is the angle between the azimuth and azimuth between the sun's position and the orientation of the building face. Okay, so this is your HSA. And similarly, it also has a component of wall azimuth and other things. Then your vertical shadow angle is used for the design of your horizontal shading devices. So then again, your DSA is this angle, which is the angle which is again determined based on the geometry of the sun position. Relate these angles for your designing of your shading devices, basically how much should be the projection and how much should be the length and other things. So again, those type of things were covered in this system, in this lecture. So we are now going to look up at assignment questions from week 2 from previous run of the NPTEL course, because the deadline for week 2 assignment has not passed yet. So we will not look up at the solutions to those questions. We will look up at the previous run of the course questions from there. And if questions are being repeated, we will omit them. So please post your answers in the chat box, or you can just unmute yourself and answer. So the first question is, in psychometric chart, a decrease in dry bulb temperature with the constant humidity ratio results in A, reduction in relative humidity, B, no change, C, increase in relative humidity, and D, none of the above. So what is the correct answer for this? So if you remember, the psychometric chart is the relationship between dry bulb temperature on the x-axis and the humidity ratio on the y-axis. And the relative humidity is in the form of these logarithmic lines with 100% as the outermost logarithmic line. Okay, so we have an answer, okay, which is correct. So basically, if you move from a higher dry bulb temperature to a lower dry bulb temperature, that is, we're decreasing your dry bulb temperature while keeping your humidity ratio constant, your relative humidity is going to increase because they are these lines. So you go from 20 to 40 to 60 and move towards subsequently. So C is the correct answer, as you correctly stated. So moving on to question 2, the unit of thermal resistance R value is A, watt per meter square Kelvin, B, watt per meter square, C, watt hour per meter square Kelvin, and D, meter square Kelvin per watt. So we are looking at thermal resistance. This can easily be confused with thermal transmittance. So thermal transmittance is 1 by R. So we are just asking what is R, the SI unit for R value. Okay, so we have an answer D, which is the correct answer. So we have R, which is expressed as the thickness of the layer divided by the thermal conductivity, that is L by K. So L is in meter and thermal conductivity is watt per meter Kelvin. So together the unit of R is watt meter square Kelvin by watt. And this is the inverse of U value, which is watt per meter square Kelvin. So this can be confused together. Again, units are important for the different parameters. Like questions like these can come in your final examinations also based on units and what are the units and the relationship between the different terms. Okay, so moving on to question 4. Increase in thermal absorptivity of a surface results in A. Decrease in solid temperature, B. Increase in solid temperature, C. Does not impact solid temperature, or D. None of the above. Okay, so solid temperature is basically the combined effect of the temperature, which includes the hypothetical temperature, which includes the combined effect of outside air temperature as well as the solar radiation effect. So this is affected by the three parameters affect the solid temperature. We have the outside dry bulb temperature, we have absorptivity, and we have the radiation, as well as the heat transfer coefficient, which is constant for a particular ambient condition of wind speed. Okay. So the correct answer is B. So all of these factors are directly proportional to solid temperature. So solid temperature is T out plus absorptivity into the global solar radiance divided by H naught, the heat transfer coefficient outside. So if you increase the outside dry bulb temperature, solid temperature will increase. If you increase absorptivity, solid temperature will increase. If you increase the global solar radiance, solid temperature will increase. All these three terms are directly proportional. So any increase in any of these terms is going to increase the solid temperature. So the correct answer is B, which is increase in solid temperature. So moving on to question 5, typically a decrease in SHGC or solar heat gain coefficient of a glass is associated with A, increase in visible light transmittance, B, reduction in energy consumption, C, decrease in visible light transmittance, or D, increase in energy consumption. This was discussed in lecture 10, I believe. Okay, so we have an answer. So this is actually both the answers, two options are correct. So solar heat gain is basically how your window blocks the direct solar radiation from the sun. So if you block the radiation, there's going to be a reduction in the energy consumption because excess heat is not being allowed inside in your indoor spaces. So occupants do not need to increase their cooling loads. That is, if the SHGC is being decreased, and then because your SHGC is being decreased, there's also a decrease in your visible light transmittance. So both energy consumption reduction and your visible light transmittance or VLT are decreased with a decrease in SHGC of your glass. Okay, usually we prefer an SHGC, a lower SHGC in buildings in hot, dry climates, particularly for this reason, such that energy and excess heat is not being allowed inside. So both B and C were correct answers. Moving on to question 6. Which of the following factors are included in estimating the thermal time constant? So you have thickness, density, specific heat, and air movement. So this is again a multiple select answer. That is, more than one options are correct. We looked up at the calculations of TTC, which was slightly complicated. Okay, so we have answers A, B, and C, which are correct. So all of these three terms relating to different layers of the building envelope are used in calculating the thermal time constant. That is the thickness of the layer, the density and specific heat of each of the layers. Also, the thermal conductivity of each of the layers is being used, as well as the heat transfer coefficient, outside heat transfer coefficient. So all the options A, B, and C are correct. So moving on to question 8. So as the temperature rises, thermal radiation produces longer wavelengths. thermal radiation stops producing any wavelength, or thermal radiation produces shorter wavelengths, or thermal radiation absorbs longer wavelengths. So we looked up at this in the radiation when we were discussing radiation, particularly heat transfer through radiation. Okay, so we have an answer C, which is the correct answer. So as the temperature rises, the thermal radiation produces shorter wavelength, and the higher the temperature of the object, the more thermal radiation is going to produce, and more heat is going to be let out by radiation. So C is the correct answer. Okay, moving on to question 9. So now we look up at calculation of U value, but this is slightly from the perspective of thermal resistance and not L by K. So we have determined the U value for the following wall section composed of three layers. So one is hardboard, which is 1/4 inch thick. Then you have expanded polystyrene or EPS, which is 2 inches thick. Then you have plywood, which is 3/4 inches thick. And the resistance of the materials per inch in FPS units are given as follows. So the R value or thermal resistance of inside air is 0.68. The R value of the hardboard, our second layer, first layer is 0.18. R value of EPS is 4. R value of plywood is 1.25. And the R value of outside air is 0.17. So U value is nothing but the sum of the thermal resistance of all of the layers, as well as including the layers of inside air and outside air. This is also a very straightforward question compared to the calculation of U value based on thicknesses and thermal conductivities. Okay, so this is also very simple. So instead of using the formula delta R, which includes the terms for L1 by K1, we just sum up the resistance of all of the layers, because we are given the resistance of all of the layers. So we have R out as 0.17. Then we have R1 as 0.18. We have R2, which is expanded polystyrene, as 4. Then the third layer is plywood, and the thermal resistance for plywood is 1.25. And then the thermal resistance of the inside air film, which is 0.68. So we add all of these thermal resistance, we get 6.28 watt meter square Kelvin per watt. This is the sum of all the thermal resistance of the entire wall assembly. And U is nothing but 1 by delta R. So 1 by 6.28 meter square Kelvin per watt. It gives us 0.159, which is close to 0.16 watt per meter square Kelvin. So we get the answer C is the correct answer, 0.16. C value can be calculated using the thermal resistance values for the different layers as well, which is nothing but the relation between L1 by K1 only. So moving on to question 10. So we have horizontal shadow angle is associated with A, the shading efficiency of horizontal shading device, B, the shading efficiency of vertical shading device, C, the altitude angle of sun, or D, none of the above. So this is from the glazing unit. Okay. So the correct answer is B. So the horizontal shadow angle, or the SHA, is the indicator of the shading efficiency of vertical shading device. So they are opposites basically. SHA gives you the shading efficiency of vertical shading device, whereas vertical shadow angle, or VSA, gives you the shading efficiency of horizontal shading device. And they use the solar azimuth and the wall azimuth in the calculation of SHA. So the correct answer was B. We would look up at the calculations of the shading device in week 3's content, particularly lecture 11. Okay, so this is all which was discussed and questions which were from the previous run of the NPTEL course. So if you have any queries or something which you did not understand throughout this problem solving session, you can just unmute yourself and ask, or you can post it in the chat box. Okay. So we also did not receive any questions in the discussion forum. So if you have any questions, you can post your queries, or if you want any clarification on concepts, you can put it in your in the discussion forums. There's a tab on the NPTEL course called Ask a Question. So you can just type your question there, and we will try to cover those questions in these sessions. That is the most effective way of using these sessions, instead of me just trying to give you an overview and asking questions. It's better that your queries are being answered based on whatever was taught throughout the week. And the lectures and slides for this presentation will be made available. I will again put the link and the link for slides and the YouTube video on the put it in the discussion forum itself, so you can access it after it has been done as well. So if there are no queries, I think we can close this session. So if you have any feedback, or if you want to see any other content in this problem solving sessions, if you have any feedback, you can again unmute yourself or put it in your chat box. Is there something which you like to see covered in these sessions? Anything else which was relevant? Okay, so if you have no other thing, so we can now close the session, I think. Thank you so much for joining the week 2 problem solving session. I hope it was useful for you.